We're going to talk now about the second law of thermodynamics, which is written here in red, and simply states that for any spontaneous process, the entropy of the universe must increase, or mathematically, delta S universe must be greater than 0. The second law of thermodynamics is simply used to determine whether a reaction will happen spontaneously, i.e. without outside intervention, or if a reaction is non-spontaneous, meaning it will not occur unless there is outside intervention. And we can see it's a very simple relationship. The entropy of the universe must increase. So entropy is really the driving force that causes reactions to happen. If we're trying to figure out what the entropy change in the universe comes from, we really just need to look at two pieces. The system, which is typically what we're interested in, and the surroundings, which is everything interacting with that system. So we need to make sure we're looking at both of these when we're trying to determine if a reaction is spontaneous or not. For the system, very simply, we just look at if the order is increasing in my system or decreasing in my system as a function of our chemical reaction. So we typically look at phase changes and how many molecules of gas. The less ordered my phases and the more molecules of gas I have, the more disordered my system is and the higher the entropy is going to be. For the surroundings, we're not actually going to look at how many molecules we have. We're going to assume that the only thing my surroundings may get from my system is heat. We're going to look at heat flow. So heat affects entropy because the more heat you have, the more energy is dispersed in a system, the faster everything's moving, and overall, the higher the entropy. So the relationship between heat and the entropy change of the surroundings is very, very simple. We can see it right here. And we can see it actually relies on delta H for the system. So we're assuming the only place the surroundings are getting any heat is from the system itself. And there are only two possibilities. If I have an exothermic reaction, my system is releasing heat and it is a negative number. So those two negatives are multiplied, and overall, we can see the entropy of my surroundings will increase, which makes sense. An exothermic reaction releases heat into the surroundings, they speed up, they move around, they get more disordered, I have an increase in entropy. Of course, the opposite can also be true. I can have an endothermic reaction where the heat for the system is increasing. Now I have a negative times a positive, which will give me a negative. So for an endothermic reaction, that's going to lead to a negative entropy change for the surroundings. The system is going to take heat from it, they're going to slow down, and my surroundings are going to become more ordered and have a lower entropy. We can see that this relationship does also account for temperature. That's simply because if you give heat to a system that's already very, very hot, it's not going to make a big difference, so your entropy change is going to be very small. Whereas if you gave heat to a system that was very, very cold, if you have a very low temperature here, that will make a really, really big difference and you'll see a large entropy change. Of course, my temperature is always in Kelvin, so my temperatures can never be negative. They start at 0 and then go up to basically infinity, but they're always going to be a positive number. So temperature is not going to affect the sign of delta S surroundings. It's only going to affect how big or small it is. So we should be able to do a couple things. First of all, we should just be able to qualitatively determine if entropy is increasing or decreasing in my system and surroundings. So let's look at an example for that. So we'll look at example 1 here. First, let's look at our system. We can see that we have 2 hydrogen molecules and 1 oxygen molecule, which combine to form 2 gaseous water molecules. Now, since all of these have the same phase, they're all gases, instead what we're going to look at is the number. So here on the reactant side, we have 3 molecules, and on the product side, we only have 2. So if we're making fewer molecules, we're creating a more ordered system, and that means the entropy for my system is decreasing. The more ordered something is, the lower its entropy. So if we're going from a less ordered to a more ordered state, that's going to be a negative entropy change. My entropy is decreasing there. For my surroundings, that's when I'm going to look at this delta H piece. We're going to keep in mind that delta S for the surroundings is given by negative delta H system divided by temperature. We're not really worried about the temperature because, again, it doesn't change the sign, and that's the only thing we're looking at. It's just going to change how big or how small it is. So for my surroundings, for this first example, there's always that negative in front, and here I have a negative delta H. Again, not worrying about the temperature because it's just going to change how big or small the number is. A negative times a negative gives me a positive. So delta S for the surroundings is going to increase, which makes sense because this is an exothermic reaction. All right, same thing for example 2. First, let's look at our system. Now this time we see that we do have a phase change. We have just gas on the reactant side, whereas on the product side we have a gas, but then we also have a solid. Solids are so much more ordered than gases that this is definitely going to be a decrease in my overall entropy. I still have one gas phase molecule on each side, but on the product side I also have this very, very ordered solid. So the product side is much more ordered, and that means the entropy decreased. Remember, entropy is a function of disorder, so if something gets more ordered, that's a decrease in my entropy. For my surroundings, I'll do the same thing I did before using this relationship up here. First I have that negative. Here my delta H is a positive. Negative times a positive gives me a negative. So both my system and my surroundings see a decrease in entropy for this second reaction. So that's qualitative, but we also want to be able to be quantitative with these relationships. So let's look at the next example. Consider the following reaction and determine delta S system, surroundings, and universe, and determine if it would be spontaneous at 298 K. First one, system's super easy. Delta S reaction here, that's actually telling me delta S system. The reaction is the system, so they're one and the same. So we can go ahead and check that guy off. For the surroundings, we're still just going to use that relationship, negative delta H system over temperature. And here again, delta H for the reaction, that is delta H for the system. Ooh, I put too many negatives in there. What am I doing? Negative delta H system over temperature. So now we just need to plug in our number. We have that negative out front. Delta H is positive 873 kilojoules. And my temperature is 298 K. I have to make sure my temperature is always in kelvins when I do this. So I just plug this guy into my calculator, and I see that it is, don't forget about that negative, it is negative 2.93 kilojoules per Kelvin. So look at both of our units there. So negative 2.93 kilojoules per Kelvin. That's delta S for my surroundings. So we can check that guy off. For the universe, it's very, very simple. Delta S universe, I just need to add up delta S for my system and delta S for my surroundings. For my system, we can see it is 187.3 joules per Kelvin. And now we have to be careful because we see that this was in joules per Kelvin, but when we did this calculation, we left it in kilojoules per Kelvin. So we need to make sure our units match. I usually think it's easier to turn my kilojoules into joules because there's 1,000 joules in a kilojoule. So to get from kilojoules to joules, I just multiply by 1,000. So in this case, instead of 2.93 kilojoules, I'll have negative 2930 joules per Kelvin. So again, I just took my negative 2.93 kilojoules per Kelvin and said there are 1,000 joules for every 1 kilojoule, and that gave me the negative 2,930. So now I just add up my two pieces, and I see that overall delta S for my universe is going to be negative 2742 joules per Kelvin. So now we got that guy. The last thing is determining if it would be spontaneous. In that case, we just need to look at the sign and remember our second law of thermodynamics, which says that if for a spontaneous process, the entropy must increase. We see that this is a negative number. My entropy is decreasing, so this guy is not going to be spontaneous. Negative delta S universe means this guy is not spontaneous. Now sometimes, after you determine it's not going to be spontaneous at a particular temperature, you ask yourself, Well, when would it become spontaneous? There has to be a temperature. Well, there doesn't have to be, but there's often a temperature at which it suddenly switches from being non-spontaneous to spontaneous. And what we can do is basically the same idea as what we did before. So we know overall the delta S universe is equal to my system plus my surroundings. And we know that the expression for my surroundings is negative delta H divided by T. So we know when delta S universe is negative, that means a reaction is non-spontaneous. And when delta S universe is positive, that means my reaction is spontaneous. So if we want to find the point at which it just becomes spontaneous, we're going to set delta S universe equal to 0. That's the point between spontaneous and non-spontaneous. Below that would be non-spontaneous, above that would be spontaneous, so 0 is just that point in the middle. So all we're going to do is set this equation equal to 0 and then plug in our information. So delta S system, that's my positive 187.3 joules per Kelvin. And then I'm going to use my expression here. Delta S surroundings is given by negative delta H over T. So my delta H is 873, so I'm going to make him negative. Now again, that's kilojoules. I want to turn it into joules, so I'm just going to multiply it by 1,000. So I'll tack on 3 zeros there. That'll be joules now. Oops. And I'm going to divide that by T, which is what I am looking for. So now it's just a matter of rearranging and solving for my temperature. So I'm going to add this second piece to the other side. So I'll get 3,000 joules over temperature is equal to 187.3 joules per Kelvin. And now, anytime you're solving for something on the bottom of a fraction and you have it like this, you can basically just swap these two pieces. So you end up with temperature is equal to 3,000 joules divided by 187.3 joules per Kelvin. So I just traded him and him. It's basically just a quicker version of cross multiplying. So now if I plug this guy into my calculator, we can see it's going to be a very large number. It's going to be 4660 Kelvin. Really, really high. So the temperature has to be really high for this reaction to become spontaneous. So now let's look at this second question. Is it spontaneous above or below this temperature? So I'm going to clear some room here. We know the temperature at which it becomes spontaneous is 4660 Kelvin. So to answer this second question, let's go back and think about the expression I had. Delta S universe is equal to my system, 187.3 joules per Kelvin, plus my negative delta H, 873, a bunch of zeros, joules, over my temperature. Overall, we want my delta S universe to be a positive thing. And we can see here we have a positive piece here, and then we have a negative piece here. I want the positive piece to win. So if I want the positive piece to win, I want this side to be as small as possible. And that's only going to happen when my temperature is really, really big. So we can see that this reaction is going to become spontaneous at 4,660 Kelvin, and it's going to be spontaneous above this temperature, because then my temperature will be really, really big. This whole piece over here will be really small, and the positive half of this equation will win out to give me a positive delta S universe.